Hello. This video we're going to look at a kinematics problem from the Cambridge text. And what I'd like everybody to understand about this problem is that it's actually a differential equations problem, but the authors anticipate that we can use our understanding of integration, our understanding of variables integration, and our understanding of chain rules, things like that, to figure out how to work with this, even if we haven't had prior instruction on differential equations. I don't know if I necessarily agree with that tack, but nonetheless, this is in the section, and it is something that we have all the tools to. We just never necessarily have seen it before. So that's why I'm putting out this video. The given information is, well, so I suppose I should go back to the beginning. We have acceleration as a function of velocity. And usually acceleration is a function of time. When we get into differential equations, usually we'll have acceleration or velocity as a function of one of the other variables, displacement or velocity, where time is implied as a variable. So we are given area as a function, or sorry, acceleration is a function of velocity, and we know velocity is a function of time. We also know that acceleration is a derivative of volume with respect to time. So this is all the information that I know going in. So what I'm going to do is I'm going to take the equation acceleration equals v squared plus 4 over 2v. Instead of writing a, I'm going to write dv dt equals v squared plus 4 over 2v. Now, at issue here is the fact that we want an expression for velocity. Specifically, we're looking for velocity squared, but you take the square root of both sides, and you have a velocity in terms of time. The solution to this differential equation is the equation for velocity in terms of time. That's what we're trying to find out. So they're telling you what your goal is. All we have to do is figure out how to get there. So here's what I see. I see dv, which represents a infinitely small change in volume, and then dt, and over here I have velocity, and over here we have velocity as an implied function of time. So what I can do is rearrange so that all the velocity variables or unknowns are on one side, and all the time unknowns are on the other. And then here's where the magic sets in. This and this are both basically derivatives, and so I can integrate both sides. On the left side I'll be integrating with respect to v, and on the right side I'll be integrating with respect to t. How do you know you can do that? Well, number one, when we see the dt and the dv, that's kind of setting up integrals for us right off the gate. Another way to conceptually understand this is the integral is like an operation, just like the derivative is like an operation, like add, subtract, square root, integrate, differentiate. It's a thing we do to things. So the notion that if I integrate this and I integrate that we'll still be the same has to be true, because if the two expressions are the same to begin with, then their integrals should be the same as well. Just equality there. Okay. On the left-hand side, it's a simple U substitution problem because there's a really nice, it's all set up just so nice for you. So quick U sub gets me the fact that the integral on the left-hand side is going to be the natural log of v squared plus 4 plus c. And on the right-hand side, the integral of 1 dt is just t. I'm going to put the constant in on the right-hand side and solve for v squared, because that's what I'm trying to do, is say v squared equals. I like where this is going because I can see an e to the t already, and I can see a 4 already, and I can see a v squared already, so I know I'm on the right track. But if I continue to solve for v squared, I've got this plus c that's still kind of pesky. It's kind of in the way. So I address that by using the product rule for exponents and break this up into the product of e to the t times e to the c. And then we subtract 4 from both sides, so now I'm left with v squared equals e to the c plus e to the t minus 4. C is that unknown constant of integration that we put over here, and t is the variable. And by the way, I only added c on one side of this equation. The reason is because it's an unknown constant. If I put an unknown constant on the left and an unknown constant on the right, then I could subtract one of them and just get an unknown constant, different unknown constant on the right-hand side. Now, the only thing I have left is to establish the fact that e to the c power has to equal 13. And that's where I use my initial condition. It says the initial velocity is 3. What does that do for me? Well, it means that since v sub 0 is 3, when I put in 3 for velocity and I put in 0 for time, I'm left with the only unknown in this equation is e to the c power, which e to the c is 13. No surprise at all, since that's what I was supposed to show. But now I've shown it, and I'm done. Thanks for watching.